Okay, so next topic is increments and distance. Say we have a particle that is moving in the plane from one point to another point. Then its coordinates will change, and the net change coordinates means with respect to two chosen axes, x-axis and y-axis. Then the net change in its coordinates are known as increments, and they are calculated by subtracting the coordinates of the initial point from the coordinates of the final point, or subtracting the coordinates of the starting point from the coordinates of the ending point. So let's have a look at this figure. Here in example 1 we have a particle that is starting its journey at this point A, which has coordinates 4 and -3, and it ends its journey at this point B, which has coordinates 2 and 5. So the increments of the particle in the x and y coordinates are respectively these differences. Here this is capital delta, which denotes the difference between two values of x. So here we are subtracting the x coordinate of the initial point A from the x coordinate of the final point. So 2 minus 4 gives us -2. So increment in the x variable or x coordinate is -2. Like that, the increment in the y coordinate is calculated by subtracting the y coordinate of the initial point from the y coordinate of the final point. So this is 8. Now what do these values tell us actually? Note that the particle has moved from A to B along a path which is somewhat arbitrary. It is not, this path does not have a standard shape. For example, it's neither a straight line nor a known curve, it's just some curve. We don't really care about the way it moves from A to B. The only things we care about here when we see the net changes in the coordinate are the coordinates of the initial and final points. What happens in between is not our concern. Now the x increment has been found to be -2. So what it means is this: when the particle moves from A to B, then you can think of it like this. Since the motion ultimately takes us to this position, so it has slid horizontally by some amount. That amount is 2, and the sign indicates whether that motion is towards the negative direction of x-axis or towards the positive direction of x-axis. Here we have minus, so it has moved in the negative direction of x-axis. That means it has got closer to the origin or closer to the y-axis. What about the y increment? Similarly, y increment tells us how much the particle is moving along the y-axis. In this case, the particle has gone up, and by what amount? By 8 units. 3 units and additionally 5 units. So that's what the increments tell us, how far and in which direction the particle is moving along each of the axes. In the second example, you see the particle starts its journey at C, which has coordinates 5 and 6, and it ends its journey at D, which has coordinates 5 and 1. So if we calculate the x increment in the x coordinate, then that is this 5 minus 5, final minus initial, this is 0. And it makes sense also because along the x-axis there has been no movement in this motion. So that's why the x increment is 0. However, along the y-axis the increment is -5. So that means it's coming down since we have minus. and by 5 units. From 6 it has come down to the level 1. Okay, from y equal to 6 it has come down to this level. So that's what increments are. Now we of course have a formal definition also. So we continue with that definition. This one, which defines increment, is not related to any motion or anything. It's related to the change in the values of a variable. So here is the definition. An increment in a variable is a net change in that variable. Now such a variable can be anything. It can actually be x coordinate or y coordinate of a point, or if you go to three-dimensional space, it may even be z coordinate of a point, or the mass of an object, the speed of an object. It can be any sort of variable, physical or non-physical, chemical, biological, anything. Okay, so net change in the values of a variable is known as an increment in that variable. So if they haven't mentioned, okay, if the variable x changes from the value x1 to the value x2, then the increment in x in x is this. You have to remember that this is final minus initial, x2 minus x1. Maybe the variable is taking, as the value is changing, you can think of this change as a change happening over some time interval. Okay, so if it is changing from x1 to x2, it may be the case that it is taking some intermediate values between x1 and x2. We don't care about those values. We only care about the initial value and the final value and the net change, because that's what increment by definition is. Okay, now we can use increments to define distance between 2 points in the plane. So let me first draw the relevant figure. So we will need 2 axes, of course. This is the x-axis, this is the y-axis. And this is the origin. Now suppose we have 2 points in the plane. We want to calculate the distance between them. Say one point is lying here, P, and it has coordinates x1, y1, and another point Q is say lying here, which has coordinates x2, y2 with respect to these axes. Now calculating the distance between P and Q is finding out the this finger is creating a lot of problems. Calculating the distance of this, calculating the length of this line segment PQ, and we can do this using increments and using the Pythagoras theorem. So what we do is this: we draw a straight line passing through P and parallel to the x-axis. Just like that, we draw a straight line passing through Q and parallel to the y-axis. These two will meet at some point, so that we are getting a right angled triangle PQ and that point. So that point also it can be given some names, say C. So if you look at this thing carefully, this is our x1 and this is our x2. On the x-axis, the real numbers x1 and x2 appear here, okay, at these points. Now, what about the length of this line segment? Joining x1 and x2. Clearly, that length is x1 x2 minus x1, because in this particular figure x2 is greater than x1, and that's because it lies to the right, x2 lies to the right of x1. So according to the way we we associate real numbers with points on the x-axis or on the real line, if we go in this direction, then the numbers increase. So x2 has more value than x1. So that's why this line segment has length x2 minus x1. And that is the increment in the x coordinate if the initial value is x1 and the final value is x2. Anyway, we also have a similar thing along the y-axis. On this level, we have y1 and here we have y2. Okay, so we have y1 here, which is also a real number, and let me write y2 here. This is the y-axis. So the length of this line segment is y2 minus y1. Now looking at the way we actually have these line segments, you can clearly see that this line segment has the same length as QC, this line segment. Like that, this line segment has the same length as the line segment PC, or the side PC of this right angled triangle. Okay, so let's also write the coordinates of C. The x coordinate of C is x2, but it's on the same level as P, same horizontal level, so its y coordinate will be the same as the y coordinate of P. So x2, y1. Okay, now this length is, although we know it is y2 minus y1, but in general let's use absolute value so that we get a non-negative real number. y2 minus y1, and this length is, this length means this length, x2 minus x1. Okay, now because we have the lengths of these two sides of this right angled triangle, where this is the right angle of course, we can use the Pythagoras theorem to calculate the length of the hypotenuse, and that will be the distance between P and Q. So we write like this. The distance between two points in the plane is calculated with a formula. The author has written a formula, but let me write calculated with the following formula. That comes from the Pythagoras theorem. The distance between P x1, y1 and Q x2, y2 is PQ. That is the length of the line segment PQ, and it's equal to this. That is, you can view this as a particle moving from say P to Q, so that you have increments in the x variable and the y variable. You take the squares of the increments, you add those two things, and you take the square root of the sum. That gives you the distance, and that is because you see this is nothing but absolute value of the x increment, and this is nothing but the absolute value of the y increment. Okay, fine, but you can ask me, where is the absolute value here? That comes simply because we have square. Delta x whole square is the same as this, and like that this is equal to and this is has they used, okay, they have not used absolute value, but you can, okay, let me just write it in a slightly different manner, then it will be more clear. We have the absolute values in the beginning itself. So this is delta x whole square plus delta y whole square, and this is equal to, if you really use the expressions for this increments, then you get x2 minus x1 whole square plus y2 minus y1 whole square. In this step, we have used the fact that if you have any real number r, then the square of its absolute value is the same as the simple square of the real number. That's what we have used. We have already seen this property before. Okay, so that is the formula for the distance between 2 points whose coordinates are given in the plane. Let's now look at example 3. It has two parts. In part A, we calculate the distance between P and Q, where P has coordinates -1, 2, and Q also has some coordinates. Is x2 minus, if you are literally using this formula, then it will be 3 minus -1 square plus 4 minus 2 square. So this is 3 plus 1, 4, 4 square is 16, and plus 4, so that is square root of 20, which is 2 times square root of 5 units. So this is the distance between P and Q. And in part B, we have a general kind of special case, a special case of this formula. The distance from the origin to the point Px, y is, the origin is O and its coordinates are, both the coordinates are 0, is OP equal to x minus 0 whole square plus y minus 0 whole square. So it's a special case of the general distance formula, where you can calculate the distance of any point from the origin. It looks like this. That is the distance value. Okay, now with this concept of increments and distance between any 2 points in the plane, we now look at graphs. Graphs in a general sense, not just graphs of functions, but graphs of relations, actually equations or relations. The graph of an equation or inequality involving the variables x and y. Is the set of all points. Px comma y whose coordinates satisfy the equation or the inequality. So that means if we are given an equation or an inequality, then we find all those points whose coordinates x and y satisfy that equation or that inequality. Those points will make a figure in the plane. That figure is the graph of the equation or the inequality. We have already done this when we, in one of the previous exercises, we drew the graph of this inequality, and the graph turned out to be this square shaped region joining the points 1, 0, 0, 1, minus 1, 0 and 0, minus 1, along with the interior of that square. So in that sense, we have the general concept of graph of an equation or inequality. And let us now see, using all the things we have seen so far, some examples where we are going to look at graphs of special types of equations or inequalities, equations and inequalities. This is example 4. Now let me first draw the figure. Here, however, I won't be able to draw things so neatly because it involves a circle. I will just roughly draw. You will be able to understand what it means. Okay, so this is a circle whose center is at the origin, and this of course is x-axis, this is the y-axis, and it has radius a, which is a positive real number. And we are saying that the circle is the graph of this equation. X square plus y square is equal to a square. So there are two parts of this example. Let a be a positive real number. Okay. The equation x square plus y square equal to a square represents those points in the plane, in the two-dimensional plane. Okay, those points, let me just write the point also here. Px comma y in the plane whose distance from the origin is, we already know what distance from the origin of a from the origin to a point is. So the distance is square root of x square plus y square, but it is also the set of points for which this quantity is equal to a square. And in general this equals absolute value of a. Remember that thing from the previous set of exercises. But now because our a is a positive real number, so absolute value of a is just a. So this equation represents precisely those points whose distances from the origin, the distance of each one of which from the origin is exactly equal to a. So that means all those points are equidistant from the origin and that distance is equal to a. So this clearly represents the circle centered at the origin and having radius a, because then you see that just like this point is at a distance a from the origin, this point is also at a distance a from the origin, and in fact all the points on the circle are at a distance a from the origin, and they are the only such points. Okay, so we have not left any point out from this list. If you look at the circle, then you see that every point on the circle has distance equal to a from the origin. The points that are lying outside the circle have more distance from the origin than a, that is, they are further away from the origin than the points on the circle are. Okay, and points that are lying inside the circle that are closer to the origin than the points that are lying on the circle. So on the circle only we have points which are at a distance a from the origin. So this equation precisely represents this set of points, and hence the graph of this equation is the circle centered at the origin and having radius a. These points lie on the circle centered at the origin and having radius a. This circle is the graph of the equation x square plus y square equal to a square. So this is one graph, or rather a type of graph, because if you change a, the circle will change in I mean its center will not change, but its radius will change. Taking a small the circle, you will have a tiny circle. Taking a extremely large, you will have a huge circle. And then part B. Part B is also related, so that's why they have been kept in the same example. It's also related to this equation, except now in place of the equation we will consider an inequality, a part of which is the equation. The points P, x, y in the plane whose coordinates satisfy the inequality x square plus y square less than or equal to a square all lie on or inside this circle. Centered at the origin and having radius a. And why is that so? It's because if you calculate the distances here, then due to this inequality, in fact let's just write the reason. This is because the distance of any such point from the origin is distance formula does not change, it is the same. However, due to this inequality, this will be less than or equal to the square root of a square, which is equal to a. So that means the distances of these points that we are talking about, whose coordinates satisfy this inequality from the origin, are all less than or equal to a. So those points can either have distance from the origin exactly equal to a, in which case they will lie on the circle, or the distances can be strictly less than a, in which case they have to lie inside the circle or in the interior of the circle. None of them will lie outside the circle. So this inequality represents, or rather the graph of this inequality is the circle along with its interior, or the disk which has the interior also, not simply the boundary. So the graph of this inequality is the circle centered at the origin and having radius a. Along with its interior. Okay, so in this case the graph has all the interior points also. The situation is somewhat like the graph of this inequality. Instead of a circle we have a square which has a particular position. Now besides the points that are lying on the square, the graph of this inequality also contains all the points that lie in the interior of the square. And in this context, before we leave this example, let's just define one thing. The circle centered at the origin and having radius 1 is called the unit circle. So when we say the unit circle, you have to understand that it is precisely this circle which has its center at the origin and it has radius exactly equal to 1. That's why it's called unit circle. Okay, then example 5. Another type of equation, another type of graph. Consider the equation y equal to x square. Some points px comma y in the plane whose coordinates satisfy this equation are these. If you have say x equal to minus 2, then square of minus 2 is 4, then y is equal to 4. So the point whose coordinates are this will satisfy this equation. Then to keep things simple, we are considering integral values of x. We can of course consider any real number in place of x. So minus 1 whole square is 1. Then we take 0. 0 square is 0. 1 square is 1. 2 square is 4. Now let's plot these points in the coordinate plane or in the xy plane. You may have already drawn the graph of this equation before. If that is the case, then you already know that it has a U shape. I think I need ink also. Okay, so this is the x-axis and so this is the y-axis. Let me put the points 1, 2, 3, 4, -1, -2, -3, -4. Two, 3, 4. Let's put 5 also. 6. Oh, -1 is here. -2, -3, minus. You understand what I mean. Okay, it's looking a little strange. Now, this point is 1, 2, 3, 4, 5, 6. So one of the points is this, which has coordinates 0, 0. Two others are -1, 1. So this is another point, and 1, 1. If we put 2, then we have 4. This is another point. If we put -2, there also we have 4. The reason we don't have a negative y coordinate of any of these points is the nature of this equation. Y is equal to x square, so the least value I can have is 0. The points will never go below the x-axis. None of the points will have negative y coordinate. So that's why I have not produced the y-axis below the x-axis much, because we don't need that place. Now if you join these points as best as you can using a graph, I have messed it up. Then you roughly get a shape like this, which will continue without any bounds in this direction, both the halves. Just like, for example, if you draw a straight line, okay, it's not bounded in either direction. So like that, this is also not bounded. It goes on and on. And this type of shape has a name. It's called a parabola. These points and all the others satisfying the given equation they make up a smooth curve. Okay, why do we bother drawing the graph of an equation? You see, when you look at an equation, just looking at the equation, you may not be able to understand much about the equation because it just involves some variable. In any part of mathematics, it's always the case that if you can somehow draw a picture, a figure that is somehow related to a given situation, then you will get a better idea of what is going on. The shape of this graph tells you a lot of things about the equation. One thing you can immediately see is that because the graph does not go below the x-axis, so the y-coordinate never assumes negative values. That is one simple thing which one can see just from the equation also without looking at the graph. But you can see that the graph has many other properties. One other property is that it is symmetric about the y-axis. If one breaks the graph in two halves and reflects one part about the y-axis, it will match exactly with the other part. If one say folds the entire plane about the y-axis, then these two halves will precisely match, and that is happening because we have square. So when you put one value of x, you get some value of y, then you put the negative of that value of x and take square, you get the precise same value of y back. So whatever your x is here, its negative also has at that point also you have the same y. So that tells us why we have this symmetry about the y-axis. And there are some other more advanced properties. We will come to that when we properly start studying calculus. These things of course are also needed, but these are only some preliminary notions that we will need. Those advanced properties tell us that this graph is, you see this smooth curve, this smooth is not just, oh, I wrote smooth. This smoothness of the curve is not just simply a thing to, it's not simply a vague, something vague to say that the curve is smooth just because it looks smooth. It's not, it does not have pointed edges like that square or any polygon may have. In that sense it is smooth, but this smooth is a technical term, and the smoothness of this curve can also be explained and understood just from the equation. However, it does not hurt to see at once that the curve is smooth. There is no jagged or pointed corners at any point of the curve. So that is related to differentiability. We will see those things later. Okay, so whenever there is a figure or some sort of visual description of something in mathematics, it always aids to our understanding, and plus it links two things. It is linking algebra with geometry. So that linkage will have its own properties, interesting properties. Okay. Then we come to the simplest types of curves, straight lines. Or I mean simplest types of graphs. So here also I have to draw a figure, so let me do that first. Okay, so this one is obviously the x-axis, the origin, the y-axis, and these are 2 points. This is P, and I have to write the coordinates. I should have drawn it somewhat larger anyway. So here the coordinates are x1, y1, and this one is, this is P1, and this one is P2, x2, y2, and we also have 2 other points. This one is P1 prime, this one is P2 prime. Okay, and here we have this point Q. The coordinates of Q are x2, y1. Will you be able to really see it? I mean, this point is P1, its coordinates are x1, y1. This point is P2. These points are all lying on the straight line, this straight line. Its coordinates are x2, y2. And what we have done, we have drawn, just like when we calculated the distance between 2 points, we completed a right angle triangle. Here also we are doing the same thing. We completed this right angled triangle. Then the coordinates of this point Q, at which we have the right angle, they will be x2, y1, and the outer, the bigger right angle triangle also we have completed. Okay, now this line is given a name also, L. Now here also, if one moves from, just like that previous distance between 2 points case, if one moves from P1 to P2, then we have increments for that movement. The x increment is delta x and the y increment is delta y. You already know what the increments are. The delta x is x2 minus x1 and delta y is y2 minus y1. Now these increments have names. Okay, in this particular case they have names. In a general case, if a point moves from a particle moves from one point to another point in the plane along some arbitrary path, then the increments are simply the x increment and the y increment. However, in this case, when the movement is along a straight line, then the increments have names. The horizontal increment is called run. Understandably, why it's called run, because the particle is running from this point to this point in its movement from this point to this point, and the y increment is called rise. How far it is rising and how far it is running. Okay, so we write like this: given 2 points, P1 with coordinates x1, y1 and P2 with coordinates x2, y2 in the plane. We call the increments delta x equal to x2 minus x1 and delta y equal to y2 minus y1, the run and the rise respectively. Between P1 and P2. Two such points always determine a unique straight line. This is a geometric fact. Okay, it's coming from Euclidean plane geometry that 2 points determine a single straight line. If you leave Euclidean geometry and go to other types of geometries, there are geometries other than Euclidean geometries, then the number of these lines between 2 points will vary. Usually called, a straight line is usually called just a line, simply a line passing through them both. we call the line P1, P2. I think these increments, the names of these increments, they are calling it run and rise. I said that this is related to a motion of a particle along a straight line and not just an arbitrary motion. I said this because this whole thing of run and rise, they are being used in the description of straight lines, but I think that is not necessarily true. Run and rise are things that are, these names in general are also given to increments for any type of motion. Why I am saying that? It's because since when we are talking about an increment, we really are not bothered about the path of the particle, and we are only concerned about the net change. So it does not really make sense to give names to this increment when we have a particular type of motion, and we don't call them by those names if the motion is of a different type. I think that's not the point. So what I said is wrong. The x increment in general is called run, and the y increment in general is called rise. Okay, we will see whether we are right about this or not. I can't remember, but we have, when we go with this idea forward, what we will have then, whether run and rise really mean in general the x increment and the y increment respectively or not, we will see that then. Now the important point here is this: any non-vertical line in the plane has the property that the ratio rise divided by run which is the y increment divided by the x increment, that is y2 minus y1 divided by x2 minus x1, is constant or has the same value for any choice of 2 points and on the line. To define run and rise and to define this ratio, we don't really need the other points P1 prime and P2 prime. However, we are saying a fact about this ratio. Okay, it's not just simply a definition. We are saying that regardless of the choice of these points P1 and P2 on the line, that is, whatever pair of points P1 and P2 we choose, they have to be distinct, of course, on the line. For them we can calculate this ratio, and the ratio will be constant. It will have precisely one value, and that value is something that says something about this line itself and not about the individual points, although the points have been used to, or rather their coordinates have been used to calculate this ratio. And the reason for this constancy of the value of the ratio is similarity of these two triangles, this right angle triangle and this right angle triangle. Why are they similar? You see, because these are similar angles, this angle and this angle, so they are equal. These two angles are equal because they are both right angles, and so correspondingly, since the sum of the three angles is 180 degrees, so these two angles are also equal, or you can also look at them as similar angles. Okay, so there is a correspondence between the angles of these two triangles which give us equal angles. So that means these two triangles, the smaller one P1 P2 Q and the bigger one P1 prime P2 prime and this vertex, they are similar. It's from that similarity that we are having this constancy of this ratio, because if you are using these 2 points P1 and P2 to calculate this ratio, then what you are doing, you are dividing rise by run. That means you are dividing the length of this side of the smaller triangle by the length of its base. However, if you use P1 prime and P2 prime to calculate a similar ratio, then the rise will be this and the run will be this, and they are similar ratios calculated for these two triangles. And because the triangles are similar from Euclidean plane geometry, we know that these ratios are equal. In fact, let's just give this one a name. Let's call it Q prime. Okay. Have they given it? They haven't given the reason here for this. Let's just write the reason, although it's simple to see by. Note that. Let's write it within brackets. Note that since the triangles P1 Q P2 and P1 prime Q prime P2 prime are similar, we have rise divided by run, that is delta y divided by delta x, which is equal to P2Q, length of this line segment, divided by P1Q, and that is equal to P2 prime Q prime divided by P1 prime Q prime. And that's why the ratio stays equal. Why did we need this non-vertical, this restriction? It's because you see, if you take a vertical line, like in example 2 we have seen this vertical line where we had this, I think it was 5, 6 and 0.51. In this case, the rise is there, or rather we have a descent, we don't have a rise, but the run is 0, because for this type of motion the x increment is 0, so we cannot form this ratio for a vertical line. So that's why we need to consider a non-vertical line. So this ratio tells us something about the straight line itself. What it's telling us is this: how much does the straight line rise for a given amount of run? If I move along the straight line, then if a point is moving along the straight line, then how much is it rising for a unit amount of run? Okay, rise per unit run. So you can clearly see that if you keep the run constant and if your rise is increasing, then the steepness of the line will increase. Okay, it will move more rapidly upwards than it is moving horizontally. So that thing is measured by this ratio m, how steep the line is. And one more thing is there, because the increments, each one of them can be positive or negative, so the sign of this ratio tells us whether the line is going up or going down. Okay, in fact that's what the next paragraph tells us. It's called the slope also. I have to say that this ratio has the same value on the line. This ratio is called the slope of the line. Slope of the non-vertical line P1, P2. The slope tells us the direction. That is uphill or downhill. Here the line is such that it's uphill. As you go towards the positive side of the x-axis, the line goes up. And the downhill will be like this. Okay, it will the point comes down as it goes towards the positive side of the x-axis. And steepness of the line. How rapidly will the point go up or down as you move along the horizontal axis? And the steepness of the line. A line with positive slope rises uphill as we move to the right, or rises uphill to the right. One with negative slope falls downhill. And why is that so? Because for a line to have positive slope, okay, by the way, as you move towards the right, then x squared, what happens to the run? What about the x increment? Say you have your point here and you have your other point, that is, as you move towards the right on the line, you will find another point. Here, for example, from this point we have moved towards the right, then on the line the point has reached this point. So this point can either be on the same level as P1, or it can be above that level or below that level. In this case, P2 is above the level of P1. So P2 can be here, or P2 can be here, or P2 can also be here at the exact same level as P1. In that case, we will have x2, y1. Actually we have y2, but y2 is equal to y1. Now, regardless of the case, as we make our movement towards the right hand side, then what is the run? Run is always x2 minus x1, and since x1 and x2 are lying on the x-axis, x2 is in this, for this type of motion, greater than x1. So the run is positive as we move towards the right. The rise, however, will depend on the case. Let us see the simplest one. If there is no rise or no fall, that is, the point is at the same level, as the original point, then rise is 0, y2 minus y1 is equal to 0. Okay. Now, if the point has moved upwards, then y2 is greater than, oh, here I have written x2, no, sorry, this is y1. Then y2 is more than y1. So this is greater than 0. And if we have this case, then the rise is negative, because here y2 is less than y1. Now, in these three cases, this one is this case, this one is this case, and this one is not this one, sorry, I think I have written no, this one is this case, this one is this case, and this one is this case. So in these three cases, if we calculate the slope, then in this case where there is no rise, the slope is delta y divided by delta x. So delta y is 0. So that means the slope is 0. In the second case, where there is a rise, the rise is positive, run is always positive. Okay, so we don't have to really bother about the run, other than the fact that to form the ratio we have to divide by the run. So rise is positive, run is also positive, so this is positive. So that's why we say that when we have positive slope, then the line rises uphill to the right. And in this case, when we have negative rise, where in fact the point falls below its original level, then the ratio is negative. So if the slope is negative, one with negative slope falls downhill to the right, and one with zero slope, although it has not been said, but it's a special situation, it does not change its vertical level. And we continue after this. The greater the absolute value of the slope, the more rapid the rise or fall. Naturally, if this value increases for a given value delta x, then it's going downhill, so the downhill it will go more rapidly. Whereas in this case, where it is going uphill to the right, if delta y increases for a given delta x, then it will go uphill more rapidly. So that increases the steepness of the line. The more the absolute value of the slope m, the more rapidly the line rises or falls. The slope of a vertical line is undefined, because in a vertical line the run is 0. We cannot divide by the run to form the slope ratio. Since in this case the run delta x is 0, and so we can form the ratio m. Okay, so that's the property of a line. Now let's see one example. For this example, again I have to draw. Let's see one concrete example where we will see two lines. One of them has positive slope and the other has negative slope, and there we will see that yes, numerically we have what we have said here, that is true actually. So how many do we need here? 7. 7, okay. 1, 2, 3, 4, 5, 6, 7 points. And on the y-axis we need 6. So the points are obtained by joining. Oh, but we need a negative. The negative part of the y-axis is also needed to some extent. 1 and 2. So the points we are joining are this. One of the lines there, it is obtained by joining this point P3, which has coordinates 0, -2, with to P4, which has coordinates 3, 6. Okay, this is white tape. And the other line is obtained by joining the point P1, which has coordinates 0, 5, to the point P2, which has coordinates 4, 2, 1, 2, 3, 4 and 2. One, 2, 3, 4, 5, 6, 7. So that is the figure. This is L1 and this line is L2. What we are going to do here is that we are going to find the slopes of these two lines. The slope of L1 is what? We use these 2 points to calculate the slope. Rise divided by run. That means y increment divided by x increment. Let's call it M1. We can directly calculate 6 minus 2 divided by 3 minus 0. So this is 8 divided by 3 and the slope of the line L2 is M2 2 minus 5. Oh sorry, am I doing it correctly? 2 minus 5, yes, rise divided by run, 4 minus 0. So this is minus 3 divided by 4. So what do these values tell us? As we mentioned earlier, first of all, let's see what the signs tell us. This is positive, so it tells us that as we move towards right, then we go uphill. The line goes uphill to the right, which you can see is the case. Here the slope is negative, so that means if we go to the right, the line goes downhill. True. And what about the values? And the values have come as ratios. That's because this is a ratio. The slope by definition is a ratio, or rather, if what can I say? A quotient. Yes. 8 divided by 3. This tells us that as we move along the line, then for every 3 units of horizontal movement, we go up, there is a vertical movement by 8 units. Okay, so if along this line, if a point is moving and you have gone towards the positive side of the x-axis by 3 units, then it does not matter from where you have started your motion, you will have gone up by 8 units. Okay, that is corresponding to a 3 unit motion along the positive direction of the x-axis. There is a 8 unit motion along the positive direction of the y-axis along the y-axis. Just like that, here the slope is negative, so it's going downhill. So, and the value tells us that as we go along the positive direction of the x-axis and we go a distance of 4 units, say, then the point comes down by 3 units. Okay, in our motion of this point along the line L2. That's what these values say. So on the line L1, y increases by 8 units as x increases by 3 units and on the line L2 y decreases by 3 units as x increases by 4 units. Okay, so these are the interpretations of these values. The direction and steepness of a line can also be measured by an angle, measured with an angle. measured by us but with an angle. The angle of inclination or simply inclination of a straight line that crosses the x-axis is the angle measured counterclockwise, or is the smallest counterclockwise angle from the x-axis to the line. To the line. The inclination of a horizontal line note that a horizontal line is the only type of line that does not cross the x-axis unless the line is the x-axis itself. Is defined to be 0 degrees. The inclination of a vertical line is 90 degrees. If phi is the inclination of a line which is some angle value, then phi is greater than or equal to 0 degree and always strictly less than 180 degrees. Now what is it that we have said here? Say this is the x-axis. Now we will look at two cases. We are talking about a line or the direction and steepness of a line. It's given by not just by slope like what we have discussed here, but also that is not the only way of saying how steep and in which direction a line is moving. We can also do that using something known as the angle of inclination. Now if a line is crossing the x-axis, either like this where it is going downhill to the right, or like this where it is going uphill to the right. If it crosses the x-axis, then the angle of inclination or simply the inclination of such a straight line is the smallest counterclockwise angle from the x-axis to the line. Counterclockwise, okay. So that means for this line, this is the inclination. This, not this one, because that is clockwise. For that one, where the line rises to the right, we have to calculate this, not this. Okay. And if the line is a horizontal line, then its angle of inclination is defined to be 0 degrees. And if it's vertical, then of course it will be 90 degrees. In any case, you can see that because we are defining the inclination of a horizontal line to be 0 degree, so you cannot continue to tilt the line like this, eventually making it coincide with the x-axis, and at the same time also increasing the angle of inclination and claiming that the angle of inclination of the x-axis is 180 degree. No. Always a straight line that crosses the x-axis means it really crosses the x-axis in this sense, not the x-axis itself. Okay, so this definition of angle of inclination for a line applies to only lines of either this type or this type. If it is horizontal like this, then the angle is 0 degree. The value of the inclination will never reach 180 degree. Okay, that is the thing. Oh, is it what? Phi is the inclination of a line, then so here in this when we study trigonometry in the next section, we will see that there we will consider positive as well as negative angles. For this one, for this particular discussion, we are not saying anything about negative angles. Okay, when we say counterclockwise like this, the angle is always positive. Oh, but it will always be positive anyway, no? Because we are not considering clockwise rotation, we are only considering counterclockwise. If these things are going over your head, what clockwise and anti-clockwise have to do with an angle being positive or negative, you just don't bother about that. The thing here is that we are measuring this angle in the sense of geometry. Okay, and that's just that's the only thing you have to know about this situation. Don't bother about the sign of the angle. We right now, for now, the angle is only the amount of this rotation. Okay, it has no sign. So although we are saying counterclockwise, but that does not say anything about the sign of the angle. We don't know anything about an angle being negative or anything like that. For us, still angle means a positive value. Okay. The relationship later, when we will study trigonometry, there we will see that counterclockwise rotation corresponds to positive angles and clockwise rotations correspond to negative angles. Because we are considering only counterclockwise rotation here in measuring the inclination of such a line. So for us, angle is always positive. The relation between the inclination phi and the slope m of a straight line is this formula, m equal to tan phi, for which of course we need trigonometry. It's not very difficult to see why that is the thing. You just have to draw another diagram. This is the x-axis, this is the y-axis, and say you have the, it will be better if I bring the line down here. So this is our straight line. Let's just arbitrarily choose one point on the line and draw a perpendicular from the point to the x-axis. And we also considered this point, the point where the line crosses the x-axis. Then this is our inclination phi. And if on this line we are using these 2 points to calculate the slope by calculating the run and rise, then this is the rise delta y and this is the run delta x. So that means what? This is a right angled triangle in which m is equal to delta y divided by delta x, and this is the length of the altitude and this is the length of the base. So from the definition of the tangent function, this equals tan phi. So that's how we get the relation between inclination and slope of a straight line. And finally, let's look at parallel lines and perpendicular lines. The idea here is just this: to understand the relationship between the slopes of 2 parallel lines, you just have to observe the fact that if 2 lines are parallel, then they have precisely the same slope because their rises and runs will be equal. Okay, if they are parallel lines, and equal in the sense that well, I should not say rises and runs are equal, but rather the ratios of rise to run, those ratios are equal. In other words, the slopes are equal, and conversely, if 2 lines have the same slope, then they are parallel. Okay, so that's what we are saying here. Lines that are parallel have equal angles. Oh, I was okay, I forgot about inclination at all. Because parallel lines have precisely the same inclinations, so that's why their slopes are the same. And conversely, if two lines have the same slope, then they will have the same inclination, and that's why they will be parallel. Lines that are parallel have the same inclination. Yeah, because if you think in terms of rise and run, then it will be difficult to see why they have the same slope. Conversely, if two lines have the same slope, then they have the same inclination, and hence are parallel. And the relationship between the slopes of two perpendicular lines, none of which is between two lines that are perpendicular to each other, none of which is a vertical line. That relationship is also there, where if you take the product of the slopes of the lines, then that product equals -1. To see why that is true, we draw one figure. But let's just write the relation first of all, and then we will see why that is true. We will justify it. For two non-vertical lines of slopes m1 and m2, we have m1 m2 equal to -1. And to see why that is the case, let's draw this figure. That is, we will draw two non-vertical parallel lines. If one of the lines is non-vertical, then the other also cannot be non-vertical, being perpendicular to that original line. So say one of the lines is this, it goes like this, and the other is perpendicular to it. And it goes like this. Okay, now say this line is L1 and this is L2. What we do, we draw a perpendicular to the x-axis from the point of intersection of these lines, and we give names also to these points: C, A, D and B. The inclination of the first line L1 is phi 1, which is this angle, and the inclination of the second line L2 is phi 2, which is this angle. Now you can see one thing, that this phi 1 is actually equal to this angle also. Why is that so? It's because this triangle ADC and the triangle CDB are actually similar triangles, where this angle CAD corresponds to the angle BCD between the two triangles. So let's write accordingly. But why are they similar? Well, their similarity is okay, let's also argue and show why they are similar. Let's not write anything about how we drew this figure. Okay, so we are not saying what A, B, C these points are. It's clear from the figure. So we will just simply argue. Note that so our concern are the two triangles CAD and BCD. If we look at this larger triangle CAB, do you see what this triangle is? It's actually a right angle triangle. Why? Because this angle is a right angle. The lines are perpendicular to each other, so this angle is a right angle. This angle is a right angle. Okay, so that means what? That means this angle is equal to 90 degree minus phi 1. Why? In triangle ABC, angle ACB plus angle CAB plus angle ABC is equal to 108 degrees. Now ACB is 90 degree plus CAB is phi 1. ABC we don't know. So from this equation it follows that angle ABC is 180 minus 90 is 90 minus phi 1. So that's how we get this angle is equal to 90 minus phi 1. Hence, in triangle, now we concentrate on the triangle BCD, that smaller triangle. So what will this angle be? if this is 90 minus phi 1 and this is 90, the sum of the three angles should be equal to 180 degree. So this has to be equal to phi 1, because phi 1 plus 90 minus phi 1 plus 90 is equal to 180 degree. So that's why angle BCD is also equal to phi 1. Okay. Now this angle which we have come to know is equal to 90 minus phi 1. It's also equal to something else. It's 180 minus phi 2. Because this is the entire 180 degree angle. From that, if you subtract phi 2, this much is left. In this triangle, what happens if we calculate the tangent of this angle? By the definition of tangent, it will be altitude divided by base. Tan 180 minus phi 2 is equal to altitude divided by base. That means CD divided by BD. Now we need to apply the formula for this expression. We will see in the section on trigonometry why this formula is true. Minus tan phi 2 divided by 1 plus tan 180 degree tan phi 2. Now tan 180 degree is 0. So that means this is equal to minus tan phi 2. Okay. So tan phi 2 is what? Tan phi 2 is the slope of this line L2. Hence, tan phi 2 is equal to minus, this is CD divided by BD. Okay. Again, in the same triangle BCD, if we calculate tan phi 1, then with respect to phi 1, the altitude is BD and the base is CD. So BD divided by CD. Now you look at these two things. By definition, or by that relation actually, this is the slope of the line L1 and this is the slope of the line L2. If you multiply them, what do you get? BD, BD they will cancel out, CD, CD they will cancel out, and you have minus 1. Hence, the product of of the slope of L1 and the slope of L2 is equal to tan phi 1 times tan phi 2. So tan phi 1 is BD divided by CD times tan phi 2 is minus CD divided by BD. This is equal to minus 1. So that's why when we multiply the slopes of two lines that are perpendicular to one another, and none of them is a vertical line, because then only we can have a finite slope, then we get minus 1. So let's end the video here. In the next video, in the next part, we will look at different types of equations of a straight line, or rather, because we are coming to these figures in the form of graphs of some equations, we will look at a particular type of equation known as a linear equation in the variables x and y, and we will see that the graph of such an equation is a straight line, and we will explore different versions of that equation and how they relate to different types of straight lines. So that will be all for calculus tonight. If you are new here and if you like these things, please consider subscribing. So that's it. This is me, Lucifer, from a mathematical room. Have a nice night.